All right, Auto One, we're going to be beginning talking about automotive batteries today. And that's our next topic after basic electricity. So an automotive battery is a lead acid battery. So it's got sulfuric acid in it, and it's got lead plates, but we'll get to that in just a moment. So it can be charged and discharged, but typically we keep it at a continuously charged state, at least ideally. But it's a chargeable and rechargeable battery. It can deliver large amounts of current or electricity, but current in particular, for let's say 10 seconds, like it says there on the screen, to up to 150, 200 amps, or even more, depending if it's a large battery, or I should really say a large vehicle. Okay. The way it's made goes like this. It's constructed with 6 cells, and each cell produces 2.1 volts of DC electricity. Okay, so we can't store AC. So it's strictly a DC battery. Let me pull this forward just a little bit. There we go. So it's strictly a DC battery, 6 cells, each producing 2.1. So a fully charged automotive battery has 12.6 volts, 6 times 2.1. There used to be 6-volt batteries way back in the day, and up until about the early 60s, mid-60s. Everything's been 12 volts since then. This automotive battery, you can see it has 1, 2, 3, 4, 5, 6 little yellow cell caps. So those are individual cells. And there's a red positive terminal, a blue negative terminal. Positive terminal is always larger than the negative terminal. Okay. So a positive plate inside each cell is made of PbO3, which is lead peroxide. Lead peroxide. And then the negative plate is made of what we call sponge or porous lead. So you've got 2 dissimilar metals in an acidic solution. You've got lead peroxide, PbO3, on the positive plate, and then you've got a negative plate, which is composed of or constructed of sponge or porous lead. Okay, so here's an automotive battery where they've cut away a section of it. You can see here's one cell here and one cell here. And you have all of these grids, these little webs of lead peroxide and porous lead. And then these are strapped together so their voltage is additive and to where it comes out where you've got about 12.6 volts. And it has plastic separators in there too. So again, a little more about battery construction. So there's insulators inside there. There are plastic insulators that keep the plates apart so that the lead peroxide and the porous lead plates don't touch. Then there's an electrolyte. An electrolyte's very, very important. That's the liquid inside. So the electrolyte is 64% water and 36% sulfuric acid, or H2SO4, in a fully charged automotive lead acid battery. So a fully charged battery, the battery is comprised, in terms of electrolyte, of 64% water and 36% sulfuric acid. So they're showing you one cell with all of its porous lead and lead peroxide plates, and then the plastic insulators, and then a positive and negative strap to connect to each of the opposing plates. So here's a little picture, and let me just do this a little bit like this. This is a little picture of the electrolyte causing a chemical, or saying that we're causing a chemical reaction. So you've got the acid reacting with these 2 plates, and there's a transfer of electrons making electricity. Okay, so this is something we can illustrate really easy with a lemon and 2 dissimilar. So what I've got here down on the table is a lemon, and I've got 2 little pieces of metal. I got a steel rod here that I'm sanding up to make sure it gets good contact with the acid. And I'll poke this guy in here like that. And then I'll take the copper here and sand this up again so it gets a really good contact. Okay, like that. And I'll go ahead and poke this guy in over here. As long as they don't touch, we're good. So there we go. Looks kind of like an alien. Well, we can help this guy out just a little bit and make him look really extra weird. And let's give him a little smile there. There you go. Okay, there's our little alien. Okay, so there's our little lemon. And we're going to make a take a 12 voltmeter, and we're going to go ahead and put this to V for volts here. And this is an automotive meter, so it's going to configure to DC volts. If I push the blue button, it says AC volts there, so now I can measure voltage coming out of a wall socket. If I go back, it goes back to DC volts. So it's jumping around because it's getting stray voltages in the air. And you should be able to see that meter. And I'll just clip this guy to that negative post, and I'll clip this guy to the positive post. And immediately we get about a half a volt, like that. And you notice it reads negative, so watch this. I'll take my leads and switch them around, and it will read positive. So I got my little lemon battery. Don't try this at home, by the way. So anyways, we got 0.519 DC volts coming out of this battery, because inside here is the citric acid is reacting with the copper, and it's also reacting with the steel. And it's actually got two dissimilar metals in the presence of an acid solution, and we are producing about half a volt. Okay, pretty cool. And then what always happens invariably, somebody says, Mr. L, how many lemons does it take to start a car? No, lemons aren't going to start cars, just FYI. Okay, we don't have enough surface area to give us enough voltage or enough current. So anyways, so let's go ahead and continue here. So what we got is, like this screen already said that we already looked at, we've got this chemical reaction happening between these plates and creating electricity, creating electron flow. So when a battery discharges, we're going to change chemical energy into electrical energy. And it's kind of cool to think that we're taking a chemical energy or chemicals and turning it into electricity. Like in a car, we take chemicals and we turn it into motion. We use oxygen in either gasoline or diesel, and by burning it, we can create a spinning motion of the wheels. So stored energy is released when this happens. When we charge, it's just the opposite. We're going to convert electrical energy back into chemical energy, and the energy is stored until we need it. So what happens over time, well, we'll talk about it a little bit more, but what happens over time is, as that's happening, there is some corrosive action that's happening that eventually wears the battery out. So when a battery is discharging, electrons are going to be drawn out of the battery to power up whatever device that we're powering up, headlights, horn, starter motor, etc. The sulfuric acid inside the battery is going to break down and create lead sulfate, which is PbSO4, which is lead sulfate, on the plates. And so it's like a crusty white coating that occurs on the plates. The percentage of acid in the electrolyte goes down, so it was 36%, it's going to start going down, and the percentage of water is going to increase as we're discharging. So acid comes out of solution and forms this sulfate on the plates and leaves behind water, and that's what happens when we discharge. Then what we say, the specific gravity decreases. So the specific gravity is the density of the liquid or the electrolyte, and we use this device which is called a hydrometer. This one's a little hard to read, but it is a battery hydrometer. And what this guy does is it will measure the density compared to water. So water has a specific gravity of 1, and a fully charged automotive battery with 36% sulfuric acid in the electrolyte will have a specific gravity of 1.30. So we can actually use that hydrometer that I have to see how charged each cell is. So when we charge a battery, electrons are going to get forced back into the battery. And what they're going to do is they're going to knock that sulfate off back into solution. So the sulfate's going to leave the plates and mix with the water and then once again form acids. So we say that the percentage of acid goes up and the percentage of water goes down and the specific gravity increases. So it's exactly the opposite of discharging. Okay, so again, the electrons are going to force the sulfate off the plates, and they're going to mix back in solution as increased acid, decreased water, and the specific gravity is going to increase. And that's what happens when the battery charges. So when we discharge too much, we make a lot of sulfate, and as we're recharging, some of that sulfate falls to the bottom between the cells and eventually over time starts shorting out the plates so they don't make as much electricity. So the simple thing that you can do to preserve the life of the battery is to make sure that that you don't discharge the battery. In other words, you don't leave your lights on and drain the battery down. And also you need to keep it full of water. Like you remember in our fluid level inspection back at the beginning of the term, we wanted to make sure that the water was about 3/4 of an inch from the top, or just when we get the meniscus, when the water hits the bottom of that cell cavity, which is about 3/4 of an inch down. All right, let's continue on here. So a battery wears, like we're saying, when we excessively discharge the battery. So when we say age, what occurs because of the age is the encrusting of the plates. But if you keep the battery full of water and always fully charged, it's amazing how long the batteries will last. They typically come with an 84-month warranty, which is 7 years. And a decent battery usually will last the full 7 years as long as it's not discharged over and over again excessively or something like that. Okay? The plates short out when the material falls down, when excessive sulfation falls down between these plates. Material falls down there and will short across those, and then the battery doesn't want to do its job. Okay? Or it doesn't produce enough voltage. And this is just a simple picture just showing you, okay, we got a charged battery where we got 36% acid and 64% water and got our dissimilar metal plates. It discharges by lighting up a light, goes to a discharge state, and then of course we charge it with an automotive alternator, forcing electrons back in, knocking the sulfate off the plates, and the acid goes back into solution. Okay, so let's talk just a little bit about battery maintenance. So this happens to be a side terminal battery that General Motors used for a lot of years. They're kind of problematic. It was a good idea thinking, oh, we'll bolt the cable on, but the contact area wasn't so good, and this little 8mm head bolt tends to strip, and everybody hates them. But anyways, we got to make sure the cable connections are clean and tight, clean underneath where it attaches to a lead terminal there, and the ground is clean and tight as well. We always want to make sure that the electrolyte is up to the bottom of the cell, which is about 3/4 of an inch from the top, and we get that meniscus. So the acids just touch the split ring on the top of the case. So usually there's a cavity coming down, and as soon as it gets to the bottom of what they call the split ring, you get a meniscus, and you can see that you're full. So there were some batteries that had what's called a charge indicator, or a green eye. General Motors did this. Right on the top of the battery, you could look down through this little sight glass. If it was green, it was supposed to be fully charged. If it was dark green or not visible, it needed to be charged. And if it was yellow, you were supposed to replace the battery. In my opinion, I would not pay attention to this, okay? Because I don't think it's really that accurate, okay? You don't see these anymore. I haven't seen one for a long time, but once in a while, you'll see one. Okay, so battery terminals is how we connect the battery to the engine, etc. So here's a top post battery with our two terminals, positive and negative, positive always being larger than the negative. Here is a side terminal battery. These are the ones that get bolted on. This one has a cap that removes, this one has a cap that removes. It covers 3 cells, and this one has individuals. But sometimes these covers are non-removable, and we call that a maintenance-free battery. I'm not a fan of maintenance-free batteries because they seem to not last as long as the ones that you can add water to. That just makes me think that a little bit of the water is able to evaporate out of there because it isn't a perfect seal. Okay. So different types of battery cables. You don't necessarily need to write this down, but just to show you, these are regular old school top post battery cables. This is a bolt-on style. This is a side terminal bolt-on style. This is what your modern Um, Battery cable looks like very, very thin treated steel or sometimes treated copper to prevent corrosion. But these are just lighter, and they're going to try and reduce material for cost and weight, material for weight as often as they can. Okay, so just different types of battery cables that you'll see, but this is the more common one, and it happens pretty frequently. After 10 years or so, these will crack, and then you've got to replace it. So a little bit about battery ratings here. So the warranty of a battery goes like this. It's the battery life in months. So an average battery has a warranty of maybe 84 months, which is approximately 7 years. Okay, and so that's how they sell. Oh, this is an 84-month battery, or this is a 72-month battery, etc. The group number refers to the size or the case dimensions, and it also refers to the orientation of the positive and negative posts. So, for example, this one down here, if it wants to focus, so it's not focusing real good. Give it just a second. It should. Okay, I think it's focused pretty good. So here's the negative cable, and here's the positive cable of this battery that's been all taken apart. And so the negative could be here, it could be over here, etc. So there's different orientations, and that's determined by what's called the group number of the battery. Hopefully this thing wants to focus a little bit better. We've been having some issues with focusing lately. Okay. All right, next is what's called the reserve capacity. So the reserve capacity is how long the car will run on the battery alone. So if you're driving home from Santa Barbara, all of a sudden the charge light comes on, which means the alternator is not charging the battery. It's not a battery issue, it's a charging system issue. You've got, if the reserve capacity is 1.5 hours, then you've got 90 minutes theoretically to drive that car before it shuts off, because the battery won't have any more power to run the ignition system and the computers. That, of course, depends on whether you got the headlights on, or you've got the windshield wipers on, or you're playing the stereo, etc. So if the charge light comes on, it makes sense you turn off any unnecessary electrical devices, unplug your power points, and turn your stereo off so you can get as far as you can. But the reserve capacity is how long the battery will power the car without the alternator charging it. Okay, so cold cranking power or cold cranking amps is a way of rating a battery. So this is the number of amps that a battery can supply for 30 seconds at 0 degrees Fahrenheit. So that kind of temperature doesn't make a lot of sense to us because we don't get that cold, but in the Midwest or in the upper Midwest, where it gets quite cold in the wintertime, you come out to a car and have to start it at 0 degrees. That's a real issue. So you've got to have a battery that produces enough cold, what we call cold cranking amps, or provides enough current at a cold temperature to actually be able to start the car. So we usually say that this should match or exceed the cubic inch displacement of the engine, but that's kind of an old school rule of thumb, because a modern engine may only have 140 cubic inches. We need a battery with quite a bit more than 140 cold cranking amps. Usually batteries are rated to they're usually like 500 to 700 cold cranking amps. 600 is kind of a common rating. A little bit about battery testing. So we're going to test the battery with what's called a hydrometer, and that hydrometer is going to measure the specific gravity of the electrolyte. It's given us an idea of how charged each individual cell is. Most technicians don't use these, but stores that sell batteries will, because when they get one that comes back and somebody says it's defective, they can quickly check the cells. And once in a while you'll find a battery that has a bad cell. It's shorted together at the bottom, and the specific gravity in that cell isn't good. Normally, when we have low specific gravity, it's low on all the cells. We want to top off the water. We want to charge it low and slow, like a half an amp for 8 hours or something, and then retest the battery. Usually they're okay. It should be 1.250 or more. 1.30 is a fully charged automotive lead acid battery. We can do what's called a load test, and this is not something we typically do in this class, but I just want you to know that it's something that can be done. The load test is going to say, we're going to use this machine to see how much amperage the battery can deliver for 15 seconds. Now this is an old school machine. These Sunbat 40s are an analog meter, but they still work really well, and they're nice for teaching because students can see the needle and kind of see what's going on, whereas a lot of modern testers, you can't really see what's going on, it just gives you an output. In order to do a load test, each cell's got to be at least 1.250 or more. If it's not, we know it's going to fail, so we need to fill it with water and charge it up first and then do the load test. And what the load test, how it works, we're going to discharge the battery at 1/2 of its cold cranking amp rating. So if it's a 600 cold cranking amp battery, we're going to draw 300 amps out of it, and we want to see that the voltage doesn't drop below 9.6 volts in 15 seconds. Okay, so we want to see if this voltage, while we're pulling 300 amps, can maintain 9.6 volts minimum or more for 15 seconds. Now, if it goes down to 9.6 volts and it only got up to, let's say, 200 amps, your final reading is 200 amps at 9.6 volts. If it got to 300 amps, which is what you were hoping for, at 10 volts, that's great, or even 10.5 volts. But if it only got to 200 amps at 9.6 volts, a lot of students ask me, well, do I need to replace the battery? And I say, well, let's say it's a little Honda or Toyota, and it's starting the car fine. And I'd say, well, the battery's performance is reduced, but it's still working fine, and the 200 amp output, which would be roughly 66% of its output, or 2/3 of its output, is sufficient for that car. But you just know, hey, and I look at the date code on the battery and I go, oh, it's a 5-year-old battery and it's a 7-year warranty. Okay, it's getting old, but it's still doing the job. Maybe I wouldn't replace it if I'm just driving around town, but maybe I would if I was planning a big trip in the summertime, or in the wintertime, more like across the country or something like that. All right, that's it for now. We'll do some demonstrations and show you how to service the battery.